my name is Nitya from MIT, and today I'm going to talk about some joint work with Yoji, Dingding, Bernard, and Yufei, showing that almost all KSAT functions are unate. Before I get started, let me define what a KSAT function is. So a KSAT function is a special class of Boolean functions. So when I say a Boolean function, I mean a function that takes in as input n Boolean variables, which we'll think of as very large and going to infinity, and spits out either 0 or 1, or true or false. And a KSAT function is a type of Boolean function that can be represented as a KDNF or KSAT formula. So what is that? So a KDNF formula is a formula that consists of a bunch of clauses. So you can see here that there's a formula f in the example that's made up of 3 clauses, although a 3-sat function can have any number of clauses. The number 3 refers to how many literals appear in each clause. So you can see here we have a collection of clauses. Each clause is comprised of 3 literals, and each clause is the and of 3 literals. And a KDNF formula is the or of a bunch of these clauses, each of which has k literals. So what this means is that in order for this function f to evaluate to true, there must be at least one clause such that all of the literals in that clause evaluate to true. So you can see that we have literals that correspond to the positive version of variables, and this line on top means that we negate the variable. So in theoretical computer science, it's often more common to think of KSAT formula in terms of their conjunctive normal form, or CNF form. But in this talk, we're going to be interested in the question of enumerating the number of functions. And since if we take kind of a formula f and we negate the formula, if we start with a KDNF, we get a KCNF, for the purposes of enumeration, it's equivalent for us to think about either counting CNFs or counting DNFs. And we'll focus on counting formulas in DNF form in this talk. So there are 2 motivating questions for this talk. And it turns out that in answering the first, our result will be structural enough that will sort of give some insight into the second kind of more vague question. The main question that we're going to try and answer in this talk is, if we think about k as some fixed quantity and the number of variables n is going to infinity, how many KSAT functions are there? And motivated by this, we're also interested in what does a typical KSAT function look like, and in fact, what are good definitions for the word typical or look like. So before we kind of dive into trying to give an exact or asymptotic enumeration of KSAT functions, let's start with some simple bounds. So maybe we can start by trying to give an upper bound on how many KSAT functions are there. Well, all KSAT functions are Boolean functions. So there's at most 2 to the 2 to the n KSAT functions, which is the number of Boolean functions. However, as we might expect, most Boolean functions do not have a representation as a KDNF formula. So one simple upper bound we can give is that the number of KDNF clauses, like how many ways are there to kind of pick one of those clauses? Well, there are 2n different literals, and we have to choose k of them. So if we imagine whether or not they're imagine we don't even require them to be distinct, there's at most 2n to the k different clauses, and each formula is determined by sort of specifying some subcollection of these. So the number of KSAT functions is certainly at most 2 to the 2n to the k, and this is not exactly a tight upper bound, but this is much, much smaller already than our first upper bound. But it turns out that we can, hope to even improve this upper bound. Because you could have multiple different formula that look visually similar, but actually correspond to the same Boolean function. So in this example, you can see that this first formula on the left is the same Boolean function as the formula on the right. They're different formula, but x2 and x3 are playing the role of dummy variables. They don't actually affect the outcome of what the function gives. So this is kind of like a degenerate way in which different formula could look different but correspond to the same function. But it's a natural question to ask, which is sort of how good is our upper bound? How much redundancy is there in kind of these KSAT formula giving functions? So to try and answer that question, we can try and come up with a lower bound. So what does it mean to come up with a lower bound? Well, we can try and explicitly give some class of formula where we promise you that in that class of formula, each formula corresponds to a unique Boolean function. So one very natural class are the class of monotone formula. So a KDNF formula is monotone. All that means is that no variable is negated. So I have, a bunch of clauses, and the only literals that appear in that clause are the positive version of variables. So there are n choose k monotone clauses on n variables, and so the number of monotone KDNF formula is 2 to the n choose k. And as it turns out, each monotone KDNF encodes a distinct k-sat function. Why is this the case? Well, let's kind of consider an example. So I have two different monotone KDNF formula, phi1 and phi2. If they're different, there must be some clause that appears in exactly one of the formula. So in this case, the underlined in blue clause, x1 and x2 and x3, appears in phi1, but not phi2. But now, how can I certify that these two formula correspond to different Boolean functions? Well, I can just find some input, some assignment of the variables, such that phi1 and phi2 spit out different answers. And the assignment I'm going to choose is the one that satisfies this clause, i.e. assigns x1, x2, and x3 to be true, and all other variables to be false. So importantly, this assignment, the only monotone clause it satisfies, is this blue clause, and therefore it makes phi1 true, but phi2 false. And this tells us that these two kind of formula are different functions. And you can do the same for any kind of pair of distinct monotone formula. Now we can improve this lower bound a little bit by using the fact that it wasn't actually very important in that proof that, all the variables were positive. In fact, if we required all the variables to only appear in their negative form, the proof would have worked just as well. So we can extend the class of functions slightly to the class of unate formula. So a KDNF formula is unate if I can negate a subset of the variables and make it monotone. What that means, in other words, is that there's no variable that appears in the formula both as like plus x and as not x. That appears both in its positive and negative forms. And, you have to be a little bit careful about counting, but roughly speaking, there are 2 to the n ways to choose an assignment, to choose like which of the positive or negative literal I'm going to take of each variable. And so that gives me that roughly the number of unate k-sat formula is 2 to the n plus n choose k, up to a multiplicative 1 plus little o 1 factor. And it turns out, for a similar reason, that all unate k-sat formula also correspond to distinct functions. So pictorially, what do we have? So I'm going to use circles to describe functions and squares to describe formula, because as we've seen earlier, there's not exactly a one-to-one correspondence. So we have some big space of all Boolean functions. We know that there's some smaller sub-collection that corresponds to the k-sat functions. Separately, we have like a relatively big collection of k-sat formula, not all of which correspond to unique functions. Within the set of k-sat functions and k-sat formula, we have the unate formula, which are in one-to-one correspondence with distinct Boolean functions, and we call these the unate k-sat functions. Right? Each unate formula gives us a different Boolean function. And we know that if you look at this bottom right square diagram, that the unate formula are a very, very small piece of the number, in the space of the number of k-sat formula. Most k-sat formula are not unate. The question that we're going to sort of answer in this talk is, what about the setting for functions? Even though there are not that many k-sat formula, do they actually capture most of the possible Boolean functions that we could get from a k-sat formula? In other words, if we look at the light blue shaded region between the blue circle and green circle, how big is it? How many k-sat functions do we miss if we only restrict ourselves to the unate k-sat functions, keeping in mind that we've missed most of the possible formula? It turns out that the lower bound we came up with is asymptotically we're going to show it's correct. And Balogh, Brightwell, and Lidick in 2003 conjectured this, in fact, this very sharp conjecture, that the number of k-sat functions is, in fact, at most 1 plus little o1 times the number of unate functions. So, in fact, this blue circle is only little o1 away from this green circle. And the main result is that we verify for all k that this Balogh, Brightwell, Lidick conjecture holds. It was formerly verified in the case of k equals 2 and k equals 3 by Allen, Illenkamp, and Kahn, and we verify it newly in this work for all k greater than or equal to 4. This is sort of a product of 2 distinct pieces of work, one of which is at STOC, but for the rest of this talk, what I want to do is tell you a little bit about the proof. So how is our proof going to proceed? So we're going to have several steps. The first thing that we're going to want to do is we're going to try and reduce this task, which is counting all of the KDNF formula that, kind of encode all KSAT functions, to trying to find some smaller subcollection of the set of green formula that we're sure include all of the different KSAT functions. And what do I mean by this? We're going to choose the class of minimal formula. So this is going to sound almost like a tautology at first, but I'll kind of explain why this sort of definition is interesting, which is we'll say that a KDNF formula is minimal if whenever I delete any clause from that formula, I get a different Boolean function. So a different way to think about this is that non-minimal formula have some redundant clauses. So they have some clause that if I satisfy that clause, I must also satisfy some other clause in this formula. So you can see in this example, the first clause is redundant because if I assign this first clause to be true, I have to make x1, x2, and x3 all true, then whether or not x4 is true or false, one of the latter two clauses will also be true. And it turns out that kind of every single KSAT function will have some representation as a minimal formula, right? Because I can just take some formula that represents that function, delete any redundant clauses, and now I have some KDNF formula whose associated Boolean function is whatever function I cared about. And so it suffices for us to sort of just count, kind of how many kind of different minimal formula are there. That'll give us certainly some upper bound. And it turns out, though, that's going to be kind of too hard for us to count all minimal formula. And, that might even be apparent from the fact that this definition doesn't look like we made so much progress. But in fact, we have, because we can slightly relax this definition. We know that it is sufficient to enumerate all minimal formula. So rather than do that, we'll enumerate a slightly larger class. We'll count all of the KDNF formula that aren't obviously non-minimal. And what do I mean by that? Well, let's look at this example formula. If I ever see this example formula as a subformula of some bigger 3-sat formula, well, I know that that big 3-sat formula cannot be minimal, right? Because I have some certificate of non-minimality, some structure that's present in that big formula that would be forbidden if that formula was minimal. So in fact, what we're going to do is we're just going to count all the KDNF formula that lack some short certificate of non-minimality. And this, for those of you who are familiar with kind of extremal graph theory, is very similar to questions that are asked about trying to count, for example, graphs that are free of some, single or small collection of forbidden subgraphs. And so actually, what we're going to do is we're going to go from counting 3-sat functions to counting minimal 3 DNFs to actually what we're going to count, in the case of k equals 3, is the number of 3 DNFs that essentially lack this exact particular subpattern. All right, so that takes care of step 1. And now, like I said, there's some sort of analogy we can make to graph theory, and we can try and make this analogy more precise. And the way we're going to do that is we're going to associate a hypergraph-like object to each KSAT formula. It's maybe unsurprising that we can do this. If you kind of squint at a formula a little bit, and it's like a bunch of, clauses, each of which is made up of k things, this sort of seems like a k-uniform hypergraph. And so what we're going to do more precisely, although I won't actually be totally precise about the association, is we're going to define an object called a k-PDG. A k-PDG stands for k-partially directed graph. So what this means is it is, a k-uniform hypergraph. So it's some collection of vertices, which are like variables or points, and some collection of edges. And each edge is a collection of k distinct vertices. And we have 2 types of edges. It's called a partially directed graph for a reason. The first type of edge we have is an undirected edge. So an undirected edge is just like a set of k different vertices. The second type of edge we can have is a directed edge. Now for hypergraphs, there's many notions of what it means to be directed. The one that we're going to use in this work is that we'll say that edges are directed or pointed towards some particular vertex. So if we have a directed edge, we'll use this little hat to denote where it is directed towards. And we'll associate, in kind of some technical way, our, KSAT formulas with these partially directed graphs. And the kind of association we'll do, you can kind of imagine, for example, that this DNF we saw in the previous slide, which I've repeated here, will be associated to this partially directed triangle. So this is like some hypergraph object that looks like a triangle. It has 3 edges. 2 of them are undirected in blue, and 1 of them is directed in green towards vertex V4. And so, kind of what we're going to do is we're going to reduce the question. We first thought to count k-sub functions. And now kind of what we want to do instead is we're just going to try and count the number of partially directed graphs that are free of, this like triangle structure, this partially directed triangle. And because we will be able to formally say that whenever a partially directed graph has, many copies of this, partially directed triangle, then the associated k-sub formula will have many short certificates of non-minimality and will, not be a minimal formula. And how do we actually do this? So this turns out to be kind of very closely related to one of kind of the like sort of major areas of recent progress in graph theory, which is the hypergraph container method developed independently by Saxton Thomason and Balogh, Morris, and Samotij, where they sought to sort of answer this question in the setting of graphs and hypergraphs. And rather than kind of explain the technical details of how we count partially directed triangle-free directed hypergraphs, instead, I'm going to explain to you sort of a very classical result. And our proof is more or less proceeds along the same lines with some technical complications. So the very classical question in extremal graph theory is how many n-vertex triangle-free graphs are there? And, maybe the earliest theorem in extremal graph theory is the theorem of Mantel, which does not answer this counting question, but instead answers an extremal question, which is how big can a triangle-free n-vertex graph be? And what we've learned is that for a lot of structures, the answer to this extremal question, how big can a triangle-free graph be, and the counting question, how many triangle-free graphs are there, are very intimately intertwined. So Mantel proved that a triangle-free graph has at most n squared over 4 edges. And in fact, this is achieved by the complete bipartite graph you can see on this slide. Now note that any subgraph of this complete bipartite graph is in fact also triangle-free. So this gives us a lower bound, right? The number of triangle-free graphs is at least 2 to the floor of n squared over 4. And it turns out that this lower bound is essentially tight. Erdős, Kleitman, and Rothschild in 1973 showed that the number of triangle-free n-vertex graphs is, at most 2 to the 1 plus little o1 n squared over 4. And, as a corollary of this, they were able to deduce that almost all triangle-free graphs are in fact bipartite. Now, they proved it, and you can prove it using methods like the regularity method, but this can also be proved using the hypergraph container method, which is sort of how we proved our results about counting TK-free KPDGs. So what are the ingredients that you need to prove an enumerative result like this? So the first thing that you have to do is you have to define an auxiliary hypergraph. And we have to show that this auxiliary hypergraph is relatively regular, whatever that means. So in this case, if we're trying to count triangle-free graphs, it's a little bit confusing, but what we do is we can construct a hypergraph encoding triangles. So what do I mean by that? The vertices of the hypergraph are all the possible edges a graph could have. They're the edges of the complete graph. And the edges of our hypergraph are triangles. So what this means is that like an independent set in this auxiliary hypergraph is just a triangle-free labeled graph. And so the number of independent sets of this hypergraph is just equal to the number of triangle-free and vertex labeled graphs. So we've constructed this auxiliary hypergraph. We've checked that it's, not too irregular. In fact, for the hypergraph encoding triangles, it's like very regular. The second step is we need the answer to an extremal question, which is how big can a triangle-free graph be? We have Mantel's theorem in this case, which tells us that there are at most n squared over 4 edges. And the third ingredient is that we want a supersaturation result. And that result says that, if we want to have a strong container theorem. And that result says that if a graph has slightly more than n squared over 4 edges, so it's, required to have at least one triangle, not only does it have one triangle, but it has a cubic number of triangles. So it gets lots of triangles as soon as we're a little bit over the extremal bound. And these three ingredients, when we take them together, imply the following type of the container theorem. What they will give us is a collection of containers. So we can think of, in the case of counting triangle-free graphs, each container is an n-vertex graph that is not quite an independent set. It is, however, relatively close to an independent set in that each container has at most n squared over 4 plus little o1 edges, right? So it can't, it's not And what this means is it has a very small number of triangles by our supersaturation result. The second thing is that the number of containers we get is relatively small, right? And by that I mean we have 2 to the little o n squared number of containers. And the final result is that every triangle-free graph, or every independent set in our auxiliary hypergraph, is contained within some container. And so what this tells us is that the number of triangle-free graphs is just, at most, the number of independent sets in this auxiliary hypergraph, but each of those is within one of these containers, so this gives us the desired upper bound, which is that the number of triangle-free graphs is controlled by the size of the largest triangle-free graph. So we can do this kind of container, argument, and what it will tell us is that, like, okay, this is all very good. In fact, the number of TK-free KPDGs, or the number of kind of KSAT functions, is at most some function, like the exponential of, kind of whatever this auxiliary extremal question is, which is like the answer to some question of how big can a TK-free KPDG be. And so this is kind of the last step. And in fact, this is like kind of the main contribution of this paper at STOC. So the Turan problem that we answer is the following, which is if I have a TK-free KPDG, the number of undirected edges plus theta times the number of directed edges is at most n choose k for some theta that's bigger than the log base 2 of 3. So this might at first seem like a kind of weird extremal question, but I'm going to actually argue that it's very natural. And the reason is that if I want to take a TK-free n vertex KPDG, my TK is like kind of, it's like a triangle with one directed edge. So I could just take like a complete hypergraph where all the edges are undirected. So that's like not very interesting. And so the real question that we're trying to answer extremally is like how much can we maximize the ratio of directed edges to undirected edges, or kind of what's the maximum like kind of contribution we can get. And it turns out that this is the extremal question we need the answer to in order to make the container method work and give us an upper bound on the number of KSAT functions. Now the way that we prove this kind of auxiliary Turan problem is inspired by the method of flag algebras. But actually what we end up verifying is some local degree inequality that we verify by hand in about a page. And in fact, I'm going to, in the last kind of 2 minutes right now, explain to you. So the proof rests on the following key lemma, which is suppose I have a TK-free KPDG, which has just k plus 1 vertices, and I randomly reorder the vertices. Okay, I let x be the first k plus 1 in my random ordering. Then our key lemma is just verifying that their probability that xy forms an undirected edge plus k times theta, which is 1 plus 1 over root 2, which is bigger than log base 2 of 3, importantly, times the probability that xy forms a directed edge pointed or directed towards y, plus something that's essentially non-negative because it's a square, is at most 1. Okay? And so we prove this inequality, which you can just prove by hand because this is only like, sort of some probabilistic statement about, a k plus 1 vertex hypergraph. And then by just kind of sampling, if we have a bigger n vertex TK free graph, we can randomly subsample k plus 1 vertices and apply this key lemma, and that we can use that to determine kind of this theorem that the fraction of undirected edges plus theta times the fraction of directed edges is at most 1 for theta, which is 1 plus 1 over root 2, which is strictly bigger than log base 2. So in summary, we have this set of 3-sat formula, and we have some small collection of unate formula. We know that all the unate formula correspond to distinct Boolean functions. And in fact, we know that the number of KSAT functions is controlled by the number of minimal formula. And what we're able to show is that some slightly larger set, which is the number of 3-sat formula missing some short pattern, is in fact very close to this dark blue number of unate formula. That's all I have. Thank you so much.